it ain't going to be able to fit. So I hope that I managed to cut the slides down to what'll fit. But we'll see. So I also misplaced the dongle from my Wacom tablet, so I won't be able to scribble all over my slides today. So I was making some last minute tixie pictures, and so hopefully that'll help. Let's see. So where were we? In the first talk, I described the basic syntax of this theory, higher observational type theory that we're proposing with basic identity types that compute based on the structure of the type former. And then in the second talk, I tried to motivate why we need to add symmetries to this theory. So symmetries in the sense of transposing operations on squares and more generally on higher cubes. The squares come from dependent or heterogeneous identity types over identity types. And then I started talking at the end about the semantics that arises naturally in the category of cubical sets, or more generally cubical objects, indexed by the semi-cartesian cube category. And so today is going to be pretty much completely category theoretic, a little homotopy theory at the end. So I won't take the time to review the syntactic theory. But instead, I will start by reviewing the semi-Cartesian cubes and some of the magical behavior that they have. So I remember when I was first learning algebraic topology, I was kind of blown away by how magical simplicial sets were. Simplicial sets are kind of much better behaved homotopy theoretically than they have any right to be, than anything has any right to be. And so recently, as I've started working with these semi-Cartesian cubes, I've realized that they are also kind of magical in different ways and better behaved than anything has a right to be. So I hope to kind of convey a little bit of that. So here's the definition of this semi-Cartesian cube category explicitly. So I like the non-skeletal version. So instead of saying the objects are natural numbers, I'll say the objects are finite sets, arbitrary finite sets, and then a morphism from M to N, where M and N are finite sets, is a function back the other direction from N to M that can also take sort of plus or minus boundary values. And we require it to be injective on the preimage of M. And that injectivity is what makes it semi-Cartesian rather than Cartesian. So it doesn't have diagonals or connections, but it has symmetries and it has faces and degeneracies, of course. So there's a symmetric monoidal structure. That's the disjoint union of finite sets. The endomorphisms of any object are the symmetric group. So these are the symmetries of all. We can permute all the dimensions of any cube. And now we can consider presheaves on this category as a notion of cubical set, and that gets a day convolution monoidal structure. And then we have these basic n cubes, which are the representables in this presheaf category. And the reason we were interested in this is because not only in cubical sets, but any category that's enriched over cubical sets, as long as it has powers or cotensors by these representables, and in particular by the one cube, the interval, gives a corresponding way to represent the identity type structure that we want. So we want identity types of A that depend on two copies of A. And so semantically, that's going to be represented by this sort of path object here. This is the power or the cotensor by the interval object living over two copies of A. So this particular enriched categories that we're going to be interested in are not just the presheaf category itself, but cubical objects in some other category, E. And I'm going to actually assume that E is itself a presheaf category, just because it makes it easier to build universe objects later on. So it could be the category of sets, or it could be sort of presheaves on something or other else. And so this category is enriched, cubical objects in E is enriched over cubical sets by sort of a standard construction with mapping objects, and it has copowers and powers which are adjoint to this. So I can multiply any cubical object X by a cubical set K, and then I can also take the power or the exponential, which we denote with this pitchfork operation. And particularly important are the case when K is the one cube, the interval object, and that gives us path spaces that I mentioned before, and also cylinders, which are left adjoint to that. And we have formulas for these path spaces and cylinders as cubical objects. The formula for path spaces is sort of holds in all kinds of cubical sets, because the representables are, or so the domain category is monoidal already. And so this power by the representable is given by shifting. So an n cube in the path space is an n plus 1 cube in X. What's special about the semi-Cartesian cubes is we also have a formula for the cylinder object, which I call kind of magic. So an n cube in the cylinder on X is either an n cube in X on the left or an n cube in X on the right, or an n-1 cube in X that's sort of stretched across the cylinder. I'll draw a picture of that in a moment, but there's sort of a skeletal version here, but also a non-skeletal version where we sort of index those sort of copies of things that are stretched across the cylinder by the elements of the set N, which is often more convenient. And this magical thing sort of, as far as I know, so this is sort of only holds in the case, oh, we have symmetries, but no diagonals or connections. So here's a picture in the case of n equals 2. So a 2 cube in the cylinder is either a 2 cube on the left-hand side of the cylinder, a square, or a square on the right-hand side of the cylinder, or it's sort of a square that's stretched across the cylinder dimension. And now that's determined by a 1 cube in X on one side. And then sort of this line here is just sort of determined by a single point of X. And then this square is determined by this single 1 cube in X. And there are two copies of this. There are two ways to stretch a 1 cube across the cylinder to be a 2 cube. And the reason for that is because we distinguish the dimensions of a 2 cube. A square has two different dimensions, and we distinguish those as the first dimension and the second dimension. So in this way of stretching a 1 cube across the cylinder, the first dimension could be the one in X, and the second dimension could be the one stretched, or it could be the other way around. So that's why we need two copies of this. And the reason we really need two copies of this, because the symmetric group acts on these things, right? So we have the symmetric group on two letters acting on this whole thing. And that's just a transposition in the case n equals 2. And it acts sort of separately on these 2 cubes in X on one side, and it acts on these 2 cubes in X on the other side. But then it has to act on these stretched ones by permuting the two dimensions. And the only thing that it can do is swap these two copies of X1, because X1 doesn't actually have any action on it in X. And more generally, for n cubes, what happens is that the symmetric group on n letters permutes the ones that live all by themselves on the one side or on the other side. And then sort of a copy of the n-1 symmetric group acts on each of these guys, acting through X. And then that extra bit of Sn that's not in Sn-1 permutes these copies. And it's sort of easier to describe that in terms of the non-skeletal version. But no, we're not going to go into a lot of detail about that. But this is the picture that we should have in mind that is going to give us sort of the magical behavior of stuff. The other thing that we need is these things that are sometimes called amazing right adjoints. And this is also true for any cube category because the path space is defined by shifting. And that means it's, since colimits in a pre-shift category are pointwise, this shifting operation preserves all colimits. And so it's co-continuous, and the adjoint functor theorem gives it a right adjoint. So this path space is defined as a right adjoint, but it happens to have a further right adjoint, which is often denoted with this square root operation. We're going to use this to construct universes, which is also sort of a standard thing in cubical type theory and models of cubical type theory, to use this to construct universes. I want to mention that this amazing right adjoint also has a fiberwise version. So if I have an object over a path space, then I can apply the square root to this whole thing and get a square root of y over the square root of the path space of W. And now the square root of the path space of W, I can pull that back to W along the unit of this adjunction. So there's a map from W to the square root of the path space, and I pull y back, the square root of y back over that, and I get something over W. So this fiberwise square root acts from the slice over the path space of W to the path space, the slice over W. It's not an endofunctor anymore. Okay. So that's all the stuff that I need to know about semi-Cartesian cubes.
Mike, I'm going to interrupt you.
Yes.
Right. The semi-Cartesian cubes are the same as what are sometimes called the BCH cubes from the paper of Bazin, Pocan, and Huber, right?
Exactly. Yes.
Sure.
So that was the first cubical set model of type theory, basically, that they used that. And nowadays it's more common to use Cartesian cubes that also have diagonals. Because the diagonals certainly have advantages, but for what we're doing, the semi-Cartesian ones are the ones we want. I didn't, last time I talked a little bit about how we needed to prove the characterizations of path spaces in the semantics in order to get the computation rules for the identity types in our syntax. And I talked about briefly about how we get that for Cartesian products, because the path space functor is a right adjoint, and so it preserves Cartesian products. But more complicated is how we get the rule for function types. So this is here's the rule here for non-dependent function types, which is the simplest one. In the case of Cartesian cubes, these path spaces are just Cartesian exponentials in the Cartesian closed structure. And so they commute with these Cartesian exponentials here. And that gives us, this commutation relation here gives us the ordinary function extensionality rule that holds in Cartesian cubical sets. But in the semi-Cartesian case, this is really weird because we need to relate this Cartesian function space here with the monoidal non-Cartesian path space to get this, and this desired rule that we want has to be this funny thing that maps paths in A to paths in B. And if we translate that into category theory, what this means is that we want to pull back in this category of cubical sets or cubical objects more generally. On the left here, we have the path space of the function type, the function object, and that lives over 2 copies of the function type. And now we want this to say something about maps from paths in A to paths in B. And so that's sort of the direct thing that we can talk about is functions from the path space in A to the path space in B. But this here is an arbitrary function from paths in A to paths in B. And here what we want to get on the right-hand side here is not arbitrary ones, but they have to have F and G as the boundary, the endpoints of the path in B. So we build that by taking a pullback. So this downward map here is saying I'm going to consider the endpoints, evaluate this path in B at the endpoints. And now I'm saying I want those to be determined by these maps F from A to B and G from A to B. So this thing on the right here is basically the pullback here. And I'm saying I want this thing over here on the left, which is the paths in A arrows B to be this pullback. So this is the pullback that we want. And now I'm going to do a category theoretic calculation, which is going to prove this using this magical formula for copowers for the cylinders in cubical objects. Now, in order to use this formula for cylinders, we have to transfer things from right adjoints to left adjoints because the cylinders are a left adjoint. So what I'm going to do is I'm going to apply the Yoneda lemma. And then map into this pullback, right? So a pullback is determined by giving you a pullback when you map out of any object. And now, because these things on the right-hand side of all these Hom sets are right adjoints, I can transfer them over to the left, right? So up here, we have a map into a path space. That's the same as a map out of a cylinder. Now we have a map into a function space. That's the same as a map out of a Cartesian product, right? Because the function space is right adjoint to the Cartesian product. And similarly in all the other cases, right? So now down here on the bottom, instead of writing A to A arrow B cross A arrows B, I'm writing A arrows B squared. So this means the Cartesian square. And so then I can transfer that over to the left and write 2 times X. That just means X plus X, the co-product of X with itself. And now again, here I have a Cartesian function space on the right, and I can transfer that over to the left with a Cartesian product. And the same everywhere, right? On the right, I have a function space out of this path space, so I can move that over to the left and get a Cartesian product. Now over here, I have a path space. I can move that over to the left and get a cylinder. Here I have a Cartesian square. I get 2 copies of X on the left. I have a function type, and I move that over and I get a Cartesian product. Okay, now what's happening in all these Hom sets, I have just a B on the right. Right, and so now I can apply the Yoneda lemma again and saying that this whole thing is a pullback is the same as saying that the square of all these objects on the left is a push out. And I transposed it. So the thing that was up on the top left here is now on the bottom right, because this is a contravariant mapping out into B as a contravariant functor. So we want this here to be a push out of cubical objects. And now this is all, I'm seeing some cylinders here. And so I can hope to be able to use my magical formula. But now I'm going to, in order to do that, I've got to evaluate at n. So I'm going to take the objects of n cubes in each of these things. And now because pushouts are level-wise in a pre-sheaf category. And so now what I'm going to do is I'm going to use my formulas for how to evaluate n cubes in all of these pieces. And so let's start with the lower left here, which is the simplest one. So the n cubes in a Cartesian product are just the product of the n cubes, and the n cubes in 2 copies of x are just 2 copies of that. And now I can pull out this 2 times thing because it's just a coproduct, and a to the n, an distributes over this coproduct over here. So this is just 2 copies of xn cross an. Similar thing happens in the upper left, except that now I'm talking about n cubes in a path space. And remember, the path space is just shifting. So this is n plus 1 cubes in A here. All right. Now, now let's consider the lower right here. So again, I distribute this, and now I'm using my magical formula for the cylinder in X. I've got an n cube in the cylinder in X. So that's either an n cube in X on the left or an n cube in X on the right. So that's 2 copies of xn, or it's one of these ways of stretching an n minus 1 cube across the cylinder. So there are n different ways of doing that. And now this is a coproduct here. So my Cartesian product here distributes across that all the way into these. And now I have this and that. And you can already notice something funny is going on here, right? This here, 2 copies of xn cross an, that's exactly what I've got over here. And this map here is actually the inclusion of this sum end of this coproduct. Right, so this magical formula is already doing something magic here. Now this upper right-hand corner here is a little bit too complicated to do piece by piece, so I'm going to actually write it out as a sequence of equalities here. So I've got an n cubes in this cylinder here, and so I apply my magical formula. So that's 2 copies of an n cube in whatever this thing is, or n copies of an n minus 1 cube in whatever this thing is. Okay. And now this is a product, so I just distribute that into an nxn and this path space, xn minus 1 in this path space. And I'm now use my formula for the path space, which is given by shifting. So an n cube in the path space here is an n plus 1 cube in A. An n minus 1 cube in the path space is an n cube in A, because I sort of went down to n minus 1 because of my magical formula for cylinders. And now I go back up by 1 because I've got shifting for path spaces, and I got an an here. So now I've got this formula here. Let's put that up here. What do you know? This piece over here is the same as what I saw over on the upper left. And once again, I've just got the inclusion of this coproduct, a sum and what's left over here on the right, n copies of xn minus 1 cross an, is the same thing that I had down here. So this whole square that I got up here that I want to be a pushout is just the coproduct. I've reproduced this square up here. This is the coproduct of 2 pushout squares. This one here is the identity going from left to right, and this one here is the identity going from top to bottom. And so the coproduct of 2 pushout squares is a pushout square. So this thing is a pushout square. And then I go all the way back and I say, this is a pushout. So blah, 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 blah. This original thing I wanted was a pullback. And that's the rule that we wanted for the identity types of function types. And you can do something similar for arrow type function types in a slice category, and for pi types and so on. It's just more complicated. So somehow these magical formulas for cylinders and path spaces sort of interact in some way and make this thing come out. So this fact that this characterization was known already to BCH back then, and it was used more recently to model parametricity, or I guess actually the parametricity models in the case of the unary case instead of the binary case of cubes was already used before BCH. And I forget that it's a B, somebody in Bernardi and Cocan and Melier, BCM, I think, was the parametricity model that used something similar. It was used more recently by Evan Cavallo and Bob Harper to add parametricity to cubical type theory with one dimension of Cartesian cubes and another dimension of these semi-Cartesian ones. So I'm very grateful to Evan and Bob for sitting down with me until I could figure out a way for a category theorist to understand this. And so this is what I came up with. But I think this is just amazing that you get this magical formula here. So that's the exponentials. And now we want to talk about universes. So there's sort of a bunch of levels of constructing a universe in cubical sets. So first what we're going to do is we're going to talk about just classifying sort of what the path spaces of the universe look like without any sort of fibrancy operation on it, just sort of thinking about universes for arbitrary types, arbitrary maps in cubical objects. So again, we can sort of think about cylinders, right? So suppose I've got some type U that is some kind of a classifier of small maps. And now I want to understand the path space of U. And I want to understand it by mapping into it. And so again, this is a right adjoint. So that's the same. Mapping into this path space is the same as mapping out of a cylinder. And U classifies small maps. So what I've got to understand is a small map in the slice category over a cylinder. Okay. And now, of course, that just consists of maps at each level. And I know the n, I have this magical formula for n cubes in a cylinder, which is sort of looks like this over here on the right. And now, so what I've got is a map from yn, whatever this y is, this thing that lives over a cylinder, this object of n cubes in y maps into this coproduct. And since I'm assuming that E is a nice category, like a free sheaf topos, a map into a coproduct decomposes its domain as a coproduct. This is called the extensivity property. So Y, I can break it up into a coproduct of the parts that map to this copy of Xn, which I'm calling An, the parts that map to this copy of Xn that I'm calling Bn, and the parts that map to each of these copies of Xn minus K, which I'm calling C sub Nk. All right, so these are, at the moment, these are just objects of E. You can think of them as sets if you like, and they decompose the map on the n dimensions. But now let's think about this geometrically and put these together into some other structure. So here's a picture again, which is going to give us the idea of what happens. So here's my cylinder. I've got my, in the case n equals 2, I've got my 2 copies of x2 and my 2 copies of x1. Right. So A2 lives over x2 and B2 lives over x2. And that's going to be the same in every dimension. You've got an AN living over XN and a BN living over XN. And those ANs and BNs are sort of going to live all by themselves, and they're going to essentially assemble into a cubical object A, which maps to X, and a cubical object B, which maps to X. And those are those A and B. If you want, you can think of those as sort of what's classified by injecting X into the endpoints of the cylinder. Right, X maps into the cylinder on one side and the other side, and so you pull Y back to those two pieces, and you get an A over X and a B over X. Okay, but now, sort of, what about these other pieces? So we've got a C. I'm going to say C20 lives over this copy of X1 in the base, and also a C21 that lives over this other copy of X1 in the base. Now, however, remember that we have this action of the symmetric group that permutes, that switches these two copies of X1. And so if you think about what happens, what that means upstairs, that means that it maps, that we have a similar action of the symmetric group up here, which is essentially gives us an isomorphism between these two C objects. Right, so it maps this X1 to this X1 by the identity map. And so it has to map this object up here to this object up here by some isomorphism. So up to isomorphism was really only one object C up here. And it's acted on by the remainder of the symmetric group. Right, so we've sort of got a part of the symmetric group that interchanges these pieces. And then for general n, we also have an Sn minus 1 that acts on this Xn minus 1, and that acts on this C n here. And so that sort of already suggests that each of these C objects, Cnk, is acting kind of like the n minus 1 cubes in some additional cubical object. Now, what's left, we've sort of got the rest of these cubical operators. So we've got the cubical operators A and B, assemble them into cubical objects by themselves, but the rest of these cubical operators on the C's, we've got in particular, we've got the boundary maps that map X1 to an X0 on one side, that map X1 in the cylinder to sort of an X1 over on the side here, regarded as a one-dimensional thing. And that gives us a map from this C20 to A1 on the other side and B1 on the other side. And these are essentially going to assemble into a map of cubical objects from this C to A and to B. So this is it all written out in words, which is maybe even harder to understand. I've got a map from A to X and B to X on one side, and then I have these isomorphisms on the C's, and then what happens here, maybe I didn't really say this very clearly. So the cubical operators that act on the C's from C and K to some other C at lower dimension or other dimension, there's sort of two possibilities because there's the distinguished dimension K here. So it can either map that K to something that lands in M, and in that case, it sort of maps this C to another C and assembles it into a cubical object, or it can take a boundary and can map that K to one of these plus or minuses. And that's the case in which we do this thing where we map C to one of these A's or one of these B's. Right. And so the end conclusion, I'm not going to try to write a complete proof of this, but hopefully I've given you some intuition for that if this happens. The end conclusion is that we extract out of a map over a cylinder is a span in the slice category over X. We have A on the one side and B on the other side, and we have this other object C that maps to A and it maps to B. When we get an equivalence of categories, it's not an isomorphism of categories, it's an equivalence of categories for various reasons. But one of those reasons is that we have all these isomorphic copies of these C things that we sort of, up to isomorphism, we can ignore them and consider only one of them. And that gives us an equivalence between the slice category of cubical objects over the cylinder and the category of spans in the slice category over X. And you can actually generalize this to sort of co-powers by a bunch of other cubical sets, but this is the one that we care the most about. So why did we care about this? We cared about this because we wanted to say something about paths in the universe, which will correspond to maps into the cylinder. Right. And so it turns out what we can extract out of that is we can build a particular universe object that sort of classifies arbitrary small maps and that relates paths in the universe to the type of spans, which you can alternatively write as a type of correspondences. So given sort of two types and what this sort of correspondence or sort of proof relevant relation between them, which is sort of an equivalent way of writing a span, other type with a map to A and B. That would be the total sigma type of this. And these two types here are not isomorphic because of this sort of extra pieces of these extra copies of the C's that have to be classified separately, but we can cook it up so that there's a trivial fibration from the paths in the universe to this type of correspondences. And sort of trivial fibration basically means that whenever I have something in the codomain, there's sort of a contractible space of choices of ways to lift it to the domain. And basically that's because I've already got a classifying map for one of these copies of C. This is the one that I chose to define my correspondence here. And then I have to choose classifying maps for the other rest of those, basically. And that gives me this trivial fibration.
Mike, I'm going to interrupt you with a question from Johns Hopkins. From Johns Hopkins, Emily's group. Would the indexing category be the category of elements? I'm not sure what.
Do you mean for this K here?
Maybe they could answer. Here for the
that's my guess about what she means. So if you generalize this to some other K instead of the cylinder here, then the Ks, I don't know how to generalize it to all Ks, but to the particular Ks that have the property that the faces of a non-degenerate cube are also non-degenerate. And in that case, the indexing category that you get up here instead of the category of indexing spans is the category of non-degenerate elements in this cubical set K.
Maybe that's an answer. I have a question as well. I was expecting to see not spans, but equivalences.
Yes. So the reason
because we're missing vibrancy or something.
That's right, exactly. So the reason we don't have equivalences is because I'm classifying all maps here. Yeah. I haven't put in any notion of fibration. That's going to be the next piece. So now we're just talking about cubical sets with arbitrary cubical sets that aren't necessarily fibrant. And then this is the observation now is that the quote unquote identity types that we get are not equivalences or one-to-one correspondences, but they're arbitrary correspondences. And so really sort of what's going on here is that we get a model of a theory which is like the one that I described before, only now instead of this promote and demote mapping to one-to-one correspondences, they map to arbitrary correspondences. And that gives us a model of a theory of internal parametricity, where.
Sorry to interrupt again.
Yeah.
You're using the word correspondence in your technical sense, right?
Yes. So correspondence meaning sort of a span regarded as a type family with two indices. I'm sort of, some people might call this a relation, but it's a proof relevant relation. So I want to call it a correspondence to emphasize that it's a proof relevant relation. And as I mentioned this briefly in the first talk, there's some kind of some schools of geometers use the word correspondence to mean span. And so I'm sort of stealing that word to mean a span regarded as a proof relevant relation. The same way we can talk about a type family corresponding to sort of a map into an object of the slice category. It's a sort of equivalence, but it's useful to have a word for each way of viewing it. So in parametricity, we have a notion of sort of types are equipped with relations between them, and we want the sort of the maps to preserve arbitrary relations or arbitrary correspondences more generally. And so in internal parametricity, we have a notion of maybe bridge type. People talk about it instead of identity type. And we have a parametricity theory here where the identity types don't compute literally to the type of correspondences, but we have this sort of beta rule without an eta rule that I was talking about before, because of this notion, this fact that we have to classify these extra map copies of C. So this is the first step to a universe where we construct this parametricity universe that where the identity types is essentially acts like the arbitrary correspondences rather than equivalences. So now, as Steve was saying, we have to put in fibrancy in order to get the equivalences. So what we'd like to do is we'd like to say, I'm going to define the universe U. I'm calling U0 is this sort of non-fibrant universe. I'd like to define U to be the subtype of U0 whose identity type correspondences are one-to-one. So they have this property that on each side, the type of correspondences on the other side is contractible. And this doesn't quite make sense, but we'll be able to make sense of it. So we can say inside of the type theory what it means for a correspondence to be one-to-one, for a relation to be an equivalence, and I can interpret that. Right, so this is the other piece of this type of one-to-one correspondences that I was talking about the last couple of talks. And I can interpret that in the category that gives us an object, right? So if whenever I have a span like this or a correspondence, then I can build the type or the object that classifies assertions that it is an equivalence, that it is one-to-one. And if I do this in a slice category, I get something in the corresponding slice category. So I'd like to use this to sort of build a sort of a subtype of U0 that classifies these one-to-one, these identity types that are one-to-one. And in order to do that, I sort of want to apply this classifying construction to the universal span over U, the universal thing over this U0. And so what is this? This universal thing. So we have, it's going to be, this span is going to be obtained from some universal type family over the cylinder, because remember we said that maps over the cylinder correspond to spans or correspondences. And the way we get it is we take, all right, so the U0 is a universe, so it has a universal type family over it, so that every small family is a pullback of this. And there's an obvious map into U0 that's the co-unit of the adjunction between cylinders and path spaces. Okay, so that's a map from a cylinder into U0. So I'll take this universal type family and pull it back along that co-unit, and I get a type family living over this cylinder. And now that's an object over a cylinder, so it corresponds to a span with A0, B0, and C0 that lives over this piece here, the path space of U0. So this is the universal correspondence or the universal relation, universal span. And so I can build this classifying thing for it that lives in the slice category over the path space, because this span lives over the path space of the universe. And so we'd like to be able to sort of say this thing should be our universe, but it doesn't live over, I want to build a sub-object of U0. But this is not sort of a sub-object of U0, it lives over the path spaces in U0 rather than U0 itself. because that's where this universal correspondence is. Type theoretically, you can think of this path space of U0 is like the context consisting of two types and an identification between them. And then A0 is sort of the first type, and B0 is the second type, and then C0 is the heterogeneous identity type between them, living over that identification in the universe that comes from this correspondence thing that we talked about before. So I'd like to sort of get that now to live over U0, and we do that with this fiber-wise amazing right adjoint that I mentioned before. So remember, this square root, this fiber-wise square root takes something that lives over a path space and it maps it to something that lives over the original object. We did this sort of square root and pull back along the unit of the square root adjunction. And so now that gives me this object U1, which has the property that if I have some classifying map to U0 of a type family, then I can lift that classifying map to U1 precisely when the identity type correspondence of that type family is a one-to-one correspondence. Because sort of this thing here classifies this sort of one-to-onenesses, the fact that we have contractible everything on given one side, the thing on the other side is contractible and vice versa. All right, so this is our first attempt to make a universe whose identity types are one-to-one correspondences. However, it's not good enough. And the reason it's not good enough is because although these correspondences are one-to-one, these correspondences only themselves live in U0. We haven't done it right. The identity types of U0 live in U0. We've made the identity types of U1 be one-to-one correspondences, but we haven't done anything to make them live in U1 also. So in order for U1 to be the universe, we would want all the type families to live in U1, including the identity types. Okay, so we want to say something more about the identity types of these things, so we can do something similar with this fiber-wise square root. So instead of now building the type of classifying maps, classifying objects for being one-to-one, we'll build the classifying object for having a classifying map to U1. So we can, using the locally Cartesian closed structure, we can build a type or an object of classifying maps evaluated in U1. So U1 has a U1 tilde that I get by pulling it back from U0. And I can consider pullback squares like this, which classify C by a map into U1. And then I can build the type of such pullback squares. So I take the function type from A cross B into U1 and the function type from C into U1 tilde, and I build some pullback out of those in the locally Cartesian closed structure of my category, and that gives me a type of such pullback squares. And now I can, starting from U1, I can define a U2 such that, using this fiber-wise square root, such that the identity types of U2 are also one-to-one, so I stick this in here, and also they have a classifying map to U1. So we're basically saying, like over here, we're saying U1 is sort of the subtype of U0 whose identity types are one-to-one correspondences. And now we're saying U2 is the classified, sort of the subtype of U1 whose identity types are one-to-one and are classified by U1. Okay. Of course, that's not good enough either, because we can't use U2 now because the identity types are not U2 valued, but they're U1 valued. If I want U2 to be the universe, then the identity types should be U2 valued. So really what we do is to iterate, right? So we've got U0, U1, U2. Once we've got a UN, we define UN plus 1 to be the subtype of UN whose identity types are one-to-one and are classified by a map into UN. And then we take a limit of this tower of universes, and it all sort of works, passes all the way through, and we get a universe U whose identity types are one-to-one and are valued in the same universe U once we get to this limit. And if you compile out what this means semantically, it actually turns out to be very similar to what you get by doing a direct construction of sort of a classifier for having uniform confilling operations like you do in Orton-Pitts or LOPS way of building universes in cubical sets. And the reason for that, remember, is sort of that the way we got confillers is by transporting in a dependent identity type. All right, and so U1 has transport, U2 has transport in an identity type depending on another identity type. And that's exactly how we define the fillers for two-dimensional horns. And similarly, U3 has fillers for three-dimensional horns and so on. So you build all of this stuff in the sequential way. Yes, is that a question, Steve?
Yeah, there's a question. Remind us, is the root here the Cartesian root, or the root with respect to the Cartesian exponential, or with respect to the monoidal exponential, the pitchfork?
Monoidal, the pitchfork.
Thanks.
We don't even have a square root with respect to the Cartesian one because the domain category of cubes is not Cartesian. So the representables aren't closed in the Cartesian product. So it has to be for the monoidal one. And that's what we want, because we want this. The reason this works is that the square root has to be right adjoint to these path spaces in the universe in order to get back from the path space here and to U. And these path spaces are what are modeling the identity types for us. Okay. So now, I like this sequential limit way of thinking about things, because it's essentially meaning that U is a terminal coalgebra of an endofunctor. We've got this endofunctor that takes a UN and does this thing to it and builds a UN plus one, and we're taking this limit. So this is a terminal coalgebra. Terminal coalgebras are inductive types, co-inductive types, sorry. This co-inductive type is built out, this functor is built out of this square root. So this is a higher co-inductive type. Now, I don't want to spend a long time talking about what a higher co-inductive type is in general, but sort of basically intuitively speaking, it's a terminal coalgebra of a functor that's built using a square root. Maybe intuitively, you can say a higher inductive type has constructors whose output is an identification in the type you're defining. So a higher co-inductive type should have destructors whose input is an identification in the type you're defining. And so a map out of a path type is the same as a map into a square root type. And so you can define it using a terminal coalgebra of a functor involving a square root. So this functor here that we're taking a terminal coalgebra of basically builds in having one-to-one correspondences that are valued in the same universe. So these sort of higher destructors essentially assemble into this demote operator that we wanted, that takes an identification in the universe and gives us a one-to-one correspondence. And I don't want to go through the details of how all this works, but if you sort of take this magic cylinder formula, you can sort of transfer that over to right adjoints and tell you something about paths in the square root. And that sort of tells you that the identifications in the universe are also some kind of higher co-inductive construction. And they're defined by some similar sort of sequential limit. And that allows us to define this promote operation. So what do we want in order to model our theory? We want to be able to promote a one-to-one correspondence to an identification in the universe, which then demotes back to itself, that has this beta rule. And this map here is defined by using the construction of this thing as a limit, basically, right? So this sort of categorically speaking, this identity type is built out of, is a path space. It's a right adjoint, so it preserves this sequential limit. And then we have the formula for paths in this square root operator. So this gives us the rules that I described way back at the beginning for definitional univalence, where we have a way to take an equivalence expressed in this sort of one-to-one correspondence way and make it into an identification in the universe, and then extract out an equivalence in a way that gives us back definitionally what we started from. If we have this beta rule, but we don't get the eta rule because this IDU thing has sort of extra stuff in here that we get from this sort of sequential limit construction. We already saw that for U0, right, way back here, we already had a retraction here, which was not an isomorphism because we had to classify these extra CNs. But even if we ignored that problem at this level of fibrancy, we already also have another problem here that prevents us from having an eta rule for the universe, for ID of the universe. This higher co-induction we can also use to show that all of the type formers act on this universe, right? So we don't just want a universe object. We had to know that, say, the sigma type of something in U and a type family in U has to also be in U. And similarly for pi types and so on and so on and so on. We know that our U0 is closed under these, so we need to lift these sort of classifying maps to U, right? Over here, I've got the type of types and a type family over them, and I want to map that to a type in U. And right, U here is defined by this limit construction in the square root, so it has a nice mapping in universal property that I can use to define the sigma operator, and that's essentially using this sort of higher co-induction property. Basically, I've got to show that if I have a sigma type here, an identification between two of these guys, then if I apply sigma to them, I get a one-to-one correspondence, and sort of co-inductively, that one-to-one correspondence also has to be a sigma type. But that's precisely what we did way back in the first talk when we were defining how the computation rules for the identity types of sigma types and app on a sigma type, right? So we said the identity type of a sigma type is another sigma type. So that's sort of the recursive step or the co-recursive step of defining sigmas as a map into the universe by higher co-induction. And we said like app on the operator sigma acts like the idea of a sigma type together with sort of extra stuff for that essentially gives us the way to transport in sigma types, which we compute based on transport in the inputs A and B. And that sort of tells us basically the other part of the higher co-induction, so that we have that these identity types, the sigma takes values in one-to-one correspondences. So I'm not being very precise here because we're sort of running out of time, and I want to say a little bit of something about homotopy theory at the end as well. But basically the idea is that this endo function that we're talking about has two pieces to it: one-to-one correspondences and sort of classifying maps. And sort of these two pieces here of identity types of sigma types being also sigma types, and we're having a way to transport compute transport in sigma types is exactly what we need in order to define sigma as valued in this universe U. And this also sort of solves the problem of strictifying these identity types of sigma types. Remember where the calculating the identity types of a product type or a function type categorically, we only got an isomorphism of the path type of one object was isomorphic to the path type of another object. We want to actually compute it literally to be the other object definitionally in our syntax. And we get that in this universe U because this class of when we chose a classifying map for at each step. We sort of said, I'm going to get some classifying map from here, which is sort of isomorphic, whose pullback is isomorphic to the C that I already had. So in a sense, what's going on is we're saying that the sort of a type, something living in U, is something living in U0 together with all of its identity types that are sort of specified in a co-inductive manner. Just like a stream is a type together with another type together with another type and so on co-inductively. Here, a type in U is sort of a type in U0 together with an identity type and an identity type of that and an identity type of that and so on. So in specifying a type in U, I get to specify all of its identity types exactly. And so when specifying a sigma type, I get to specify exactly that its identity types are literally other sigma types. So that gives me this sort of coherence theorem that strictifies these computation rules. So we put all this together and we get there's some pieces here that we haven't completely finished working out, but basically in progress, we should be able to prove that we get a model of this theory, HoTT, in cubical objects in any pre-sheaf topos, and in particular in cubical sets. And so we hope that by doing some sort of gluing argument with this, we should be able to prove canonicity and normalization using these cubical sets. But I want to emphasize that we really do need symmetry here. We need symmetry syntactically in this cube category in order to interpret the pi's correctly and the universes. But we need to have symmetry and not to have diagonals. We need the symmetry in universe in syntax in order that when we do this gluing operation, we need to land in cubical sets with symmetries. And so in order for that to happen, we need the symmetries in the syntax there already. So last time I gave sort of an intuitive reason why we need symmetries in the syntax in order to compute app on REFL. But now this is sort of giving us a more stronger argument that we should, if we have symmetries, we should expect to be able to do canonicity and normalization, but not without symmetries. I don't know how to do this because we don't land in the right category to be able to interpret these identity types at all in this semantics. Okay.
Question.
Yes.
I have a question already. I'm not sure if this is for the discussion or let's try it now anyway. It's from Andy Pitts. Can you say something about the relation between the universe you just showed us and the BCH univalent universe? Are they different or are they the same?
I have not actually worked that out. I expect that they are about the same. Yeah, I mean, I think the BCH universe is built using the sort of Hoffman-Streicher kind of universe in Appreciates. I haven't been able to wrap my head around what that looks like sufficiently well in cubical sets to be able to prove this theorem about it. So I've been using the sort of the Vygotsky style well-ordered universes, but I think probably you should just be able to do something similar to make it come out. But there are different ways of making universes in general, but I think they're basically the same here.
All right, thank you.
All right, excuse me. So I've just got 5 or a little bit more than 5 more minutes. So I just want to say a little bit about models in higher toposes. All right, so one way that we could proceed to build models in higher toposes is sort of try to take diagrams in this cubical sets and so on. This syntax-like model that I talked about before, it sort of doesn't treat the symmetries equivariantly, and so we sort of don't expect it to model classical homotopy theory. There could be an equivariant version of this, like the equivariant Cartesian cubical sets that ACCRS have worked out, and that might work also. But the way that I've been thinking of doing it so far is a little bit differently, which involves you working with diagrams of spaces instead of diagrams of sets. So more generally speaking, when we define higher homotopical structures, we could work with diagrams of sets, like say quasi-categories for infinity categories, and sort of taking like simplicial sets, cubical sets, and so on. Or we could work with diagrams of spaces and then impose sort of univalence or sort of constancy conditions, which sort of reduce that down to the right homotopy theory. And here by spaces, I mean simplicial sets, which are sort of, as I said, better behaved than anyone could expect. But sort of when we talk about complete Siegel spaces as one model for infinity 1 categories, we take sort of simplicial spaces, meaning simplicial sets, and we impose sort of categorical operators on those. And that's often sort of better behaved as a model category theory. So I want to do something similar here. We're going to take a type theoretic model pre-sheaf topos. So it could be simplicial sets with the Kahn model structure, which presents the homotopy theory spaces, or it could be simplicial presheaves with a left exact localization of the injective model structure that presents any other infinity 1 topos. And now we're going to start from that model category that we know presents an infinity 1 topos, and we're going to consider cubical objects in that category. And that category has an injective model structure on itself, which that injective model structure presents the infinity 1 topos of cubical diagrams in this one that we already had, but we can localize it and get something that we would call the realization model structure, which was constructed by Vesper, and Shipley for simplicial objects, and we do something very similar for cubical objects. You get a model structure that's equivalent to the original one on E, so it presents the same infinity 1 topos. It's also a type theoretic model topos, although it's not a left exact localization of this one. And because it's cubical objects in E, sort of remember I was doing what I was doing before. I was working with cubical objects in an arbitrary nice presheaf category to build like id pi and id u and so on. And this is why I was doing that rather than just working with cubical sets. But basically all we've got to do is we've got to boost up something about the universes to say, to work with, to include extra vibrancy conditions to deal with this realization model structure. I'm gonna basically skip talking about that because I don't have time, but I can talk more about that later or in the chat or whatever. Basically, the idea is we have a classifier of realization vibrations, and then we build this sort of higher co-inductive thing, and we get a trivial vibration relating paths in this universe to one-to-one correspondences, so that we can interpret all of this higher observational type theory in some sort of model structure for any Grothendieck infinity one topos. Right. So if I've got another minute or two, will you give me another minute or two? All right. I want to end with some philosophy, because I started with some philosophy. So the question is sort of a question of what kind of type the universe should be. And sort of traditionally, a lot of people like to think of the universe as an inductively defined type, where you have sigma and pi and all the operators are constructors of this type. And then you have an eliminator, which is like the Tarski L that's sort of defined by recursion over these constructors. And it's sort of not true internally to type theory, but sort of people use this idea when they build meaning explanations, and you can build an inductive recursive universe that behaves like this. And from this perspective, you would, when we have an additional operation of identity types, you would think of it as being defined by recursion over these constructors. You would say id, right? So you have constructors id and pi and so on. So to define an operation by recursion, you would need to do clauses for what it does on sigma and what it does on pi and so on and so forth. This has some drawbacks, though, even philosophically. It's sort of it's tricky to make it in a universe like this univalent, right? If you define an inductive recursive universe naively, it ends up being non-univalent. You can play some tricks to make it univalent, maybe, but that's kind of tricky. And it also sort of suggests a closed universe, because you specified all the type formers as the constructors when you define the universe. And if you want to add a new kind of type, then you have to redefine the universe, basically. So I want to propose that it's actually better to consider the universe to be co-inductively defined, where now the Tarski eliminator L and now also our ID is a destructor. So ID is a co-recursive destructor that produces another type in the same universe. And now we can think of these type formers, sigma and pi and so on, as defined by co-recursion, mapping into the universe. And so what I would have to do to define something by co-recursion, I have to give clauses for how all the destructors act on it. So I have to say what the elements of a sigma type are, and I have to say what the identity type of a sigma type is. And that saying what the identity type of a sigma type is can be co-recursive. I can do a co-recursive call to the type I'm defining, namely sigma types. And that works because the identity type of a sigma type is another sigma type. The identity type of a pi type is another pi type, and so forth. Right. So this observation that the identity types of some type sort of lie in the same class of types allows us to regard each of them as defined by co-recursion. That explains an open universe, because if I want to define a new type former, then I just apply another co-recursion principle without having to redefine the universe. And as we've seen, it makes a little bit of sense semantically, because we actually construct this universe of vibrant types by this sort of higher co-inductive construction that sort of reifies this a little bit, at least in semantics. What I'm saying here is basically philosophical, but it sort of has this semantic version of it. And I think this gives a philosophical reason for the co-inductive behavior of the identity types of the universe with beta, but without the eta, because co-inductive types often behave like that. So let me sort of now give you a co-inductive version of Bishop's view of sets. So Bishop said a set is defined by describing what must be done to construct an element of it, and what it means to identify any two elements. So if we sort of take that seriously, propositions as types way, then what we should be doing is we should be defining a type of ways to identify any two elements of a type. And I'm going to say that sounds circular, but let's interpret it co-inductively, because that's essentially what we've just done. And similarly, we say an operation is a function if for any two elements of its domain, we have a function from identities in A to identities in B. Again, co-inductively. And this is defining the identity types together with their identity types and defining terms together with their apps. And if we just augment this with a little bit of univalence, we say we have a type U whose elements are types and in which two types are identified by a one-to-one correspondence. That's sort of the only input we have to do. We have to say what the identities in the universe are, and it's at least reasonable to say that they should be one-to-one correspondences. And then we say that every element of every type is identified with itself by reflexivity, and that gives us the type of identifications is sort of the underlying correspondence of REFL, and that sort of automatically gives us all the higher vibrancy structure. Because remember, we have sort of one-to-one correspondences in identity types, applied sort of give us singleton contractibility, which gives us all the higher con structure, and J, and so on and so forth. So this gives us a philosophical sketch of what it means to define types in a co-inductive way, which I think if you sort of try to make it precise, and sort of we spent years and years trying to make it precise, but eventually you come to HoTT, basically this theory that I described in this first couple of talks, as regarded as a theory of co-inductive infinity groupoids, which I think is really beautiful. So I'll stop there.
I think it's beautiful too. Like, it's great.
You.
Really nice. I'll just comment, and then we'll go on to the questions in the chat. That sort of thing that people have kind of intuitively been trying to do for 10 or 15 years is understand infinity groupoids co-inductively, because once you recognize that just the graph structure, right, the globular structure is co-inductive, then you say, oh, well, but now how do I get the groupoid structure in there? Kind of an infinity graph, whatever you want to call it, is a globular set. That's a co-inductive thing. And now you've got the whole thing going there. So that's quite beautiful. Okay, let's see what's happening in the chat. Here's a question from John Sterling. 2 comments. Okay, feel free to exercise. Okay, so here's the first one. Quick comment about the canonicity and normalization conjecture. I would not expect any normalization result to follow by gluing into cubical sets, because normal forms do not form only a cubical set. Normal forms must vary over a context of variables, and it's important that the pre-sheaf of variables be locally representable. Therefore, you will probably need to choose a different category. But this category will probably need to be at least cubically enriched. This, at least, was my experience from gluing configuration needed to prove normalization for cubical type theory.
Yes, I agree. I told a lie, so I didn't want to get into that. But yeah, so canonicity you can hope to get by just gluing into cubical sets. But for normalization, you need some more general kind of nerve where that maps into some kind of pre-sheaves on some kind of variable, category variables. And again, yeah, I agree. It's got to be enriched in some way, and I don't know exactly how to define it. I'm not an expert on normalization proofs, but I feel like this sort of this cubical set type construction is going to inform whatever it is you end up using in a normalization proof.
Okay, John, right on the money there. So let's see what else he has to say. I do not see why this gives a philosophical explanation of lacking eta. Co-inductive types have a universal property in semantics and thus have an eta law. We usually omit the eta law in implementations because it can make type checking undecidable, but that is an explanation by practical necessity rather than a philosophical justification for omitting eta. It seems that what is happening here is actually that we lack eta because it is not true in the model described.
Yeah, so you could You could spend an evening arguing about what's philosophical and what's technical. I mean, some people, I think, might view the fact that type theory is computational and has normalization and decidable type checking and so on as a philosophical point of view. But I can see the point, maybe. I mean, that if you do have an eta law semantically, then that sort of is not a philosophical reason to omit it syntactically. Here, I actually skipped the slide, but I have a list of all the reasons why we don't have an eta rule for idu, right? So there's all these semantic reasons here, like you said, but there's something that I didn't really talk very much about, which is that it's not that there's and sort of we're still working on the details of this, but the extra stuff that's there semantically in the identity type is actually also there syntactically, because I didn't say anything at all about how to define symmetry on the universe. So you need to be able, I talked about defining symmetry on other types, but you have to be able to define symmetry on the universe. And if you look at what is a square in the universe, if the universe did have an eta law, then the squares in the universe would not be definitionally symmetric. If you sort of to define as squares in the universe, idu to be one-to-one correspondences, then squares in the universe turn out to be sort of a heterogeneous square, which has left to right confillers and right to left confillers, but it has sort of up to down uniform fillers where you sort of have things only along the bottom line that you can fill up to the top, and only things on the top line that you can fill down to the bottom. And that's not definitionally symmetric when you transpose it. So somehow you need to, the way that I'm thinking about it right now is that idu sort of has some extra stuff in there. That's why it doesn't have an eta rule, so that the squares in the universe are actually definitionally symmetric, and the sim on the universe can sort of interchange those operations and then extract those both of those kinds of confillers. But again, we're sort of work in progress of figuring out exactly how that works. But I feel like that once you have symmetry, then at least that gives you another reason to believe that you shouldn't have eta for the universe.
Okay, that's a good answer. Thanks. I'm going to ask a question. First of all, I just wanted to clarify something on your penultimate, or maybe the one before that slide. There was what looked like a theorem or maybe a conjecture that went by really fast. Did you mean it, or were you? Go back one more. There, corollary.
Corollary, yeah.
Is that a theorem?
That one, I believe that one, I'll go out on a limb and call that one a theorem. So I believe I've actually written down all the pieces of that. Yeah, I didn't call it a theorem in progress because it's actually to me as a homotopy theorist, this one is actually easier than proving all the details of having a model in cubical sets that sort of comes from semantics, because here our fibrations are sort of defined in terms of these trivial fibrations that have lifting against arbitrary monomorphisms, and that makes it, we have a Sasinsky model structure, and that makes it a lot easier to sort of prove that things are fibrant and so on. So I feel actually more confident in this one than in the one about cubical sets that you could glue with.
Yeah, nice. Okay, great. Even though the theory itself, the type theory itself, is not fully specified yet.
Okay, well, so if the type theory is not fully specified, then this cannot possibly be a theorem. Right. You can't prove something about, yeah, but so for one particular theory, okay. I think I would say that this is true. That might not end up being the end resulting theory.
Another question, which is maybe a clarificatory one. When you showed that the path space of the universe classifies correspondences, you used your magical cylinder formula. So that looks as though that's only going to hold using the semi-Cartesian cubes where you have that magical cylinder formula. Or do you think that there's a maybe less magical proof that the path space of the universe in other cubical settings also classifies correspondence?
I don't know. I haven't really tried, but somebody at some point should try. And if nobody's done it by the time I'm done with lots of other stuff, then I might get around to trying. So I think it's a very interesting question whether a theory like this with diagonals is possible, for instance, with models in Cartesian cubes. And that would be very useful, for instance, if you want higher inductive types, because we know that higher inductive types work better when you have diagonals than when you don't. But there are various problems in the way of doing that. And one of them is that I don't know how to characterize paths in the Cartesian universe, but I haven't really tried either very hard. So I don't know how hard it might be.
Well, this is a beautiful observation, and it certainly works nicely in the semi-Cartesian case. It may be that then you can stretch it over to the Cartesian case with some hard work, but this seems to be the natural home for this result. It's very nice.
Maybe just to say, like, the other people have also sort of the semi-Cartesianness has been used in the parametricity theories, right? So the BCM, I think, that came before BCH, doing parametricity, they didn't use cubes exactly because they only had one direction of boundaries. So they were working with unary relations instead of binary ones. But they used a similar thing to talk about relations in the universe. And then what I mentioned, Cavallo and Harper used these semi-Cartesian cubes for parametricity. So,
and of course, the bicubical stuff that Licata and someone are doing uses semi-Cartesian in one of the dimensions of the thing. Perhaps for the same reason, I'm not sure. Here's another question from David Jazz. Is there a general way to add in hits into HoTT? That is, can the computational rules for id types be determined from the rules determining an inductive type?
Okay, so so ordinary inductive types and higher inductive types have different problems. So inductive types is something we're working on. I think Thorsten mentioned that in previous discussions, and I think it seems fairly likely that ordinary inductive types will work in some sensible way. So you'd like to say that the identity type of an inductive type is an inductive family somehow, like the identity types of a W type are given by some sort of indexed W type. And you have to sort of, when you have an indexed inductive type, then you sort of have transport that you sort of either want to treat as a constructor or sort of some sort of term that doesn't compute until you eliminate it on it. But there's a sort of a problem that I think we should be able to solve. Higher inductive types have this additional problem of diagonals. So if you, I'm not going to be able to describe this off the top of my head, but we can sort of work it out in the Zulip chat if people are interested. And this is again something that I learned from Evan to understand what was really going on here. In the semi-Cartesian case, where sort of what am I trying to say? When you try to compute eliminators of higher inductive types, you end up needing some kind of diagonal. At first, I thought maybe this was something special to sort of cubical type theories where things are defined using intervals, but Evan convinced me that even in HoTT, you're going to end up needing some kind of diagonal. But I think there's a chance that there's a good chance, I think, that some kind of higher inductive type will be possible using some kind of handicrafted diagonal, because we don't have diagonals in the syntax, but we can construct diagonals essentially using J, by sort of using the homotopy theory that we have, given a square, I can build a diagonal identification by just sort of composing along one side of the square. And sort of I can treat that as if it were a diagonal. It won't be as well behaved, but I'm sort of hopeful that you can at least do that to get higher inductive types. And I think it's plausible that these higher inductive types would be at least as well behaved as those in Book HoTT. They probably won't be as well behaved as those in Cartesian cubical type theory, unless we can sort of find a way to add diagonals to this theory. But I don't know, that's sort of future work.
Okay. Let's see. I'm going to ask one more question here, Mike. Do you have some thoughts about how you might implement this type theory in a proof assistant? Or have you already done it and you just haven't told us yet?
We have experimented with doing it. We don't have anything that's at a level of working. I think probably Thorsten and Ambrose could say more about this because they've done more work on that, or Ambrose particularly. But I think my sort of feel for how it ought to work is that for the most part, the rules are ordinary sort of syntax directed computation rules, right? Like when you want to compute a case analysis, what you do is look at the discriminant. If it's an injection into your coproduct, then you compute to the corresponding branch. And so sort of every active term has one of its arguments that it inspects as a discriminant and computes based on whatever that thing is. Mm-hmm. And if that thing is a variable, then it's stuck or neutral. So similarly, the subscript on id and app is its discriminant. It tells you, right, if you have an id, you look at the subscript. If you have an app, you look at the subscript, and that tells you how to compute it. And if that's that thing, whatever that thing is in the subscript is a variable, then the whole thing is neutral. And so I mean, there's going to be some the main problem that remains to be solved, I think, is how to deal with symmetry, because there are sort of most of the equational rules that we want to hold are going to be either they're basically definition rules of computation rules, or they're going to be sort of admissible rules that follow from those computation rules. But the tricky thing is going to be the rules for symmetry, because you want this sort of symmetry to commute with app, and you want this sort of braid equation to hold for symmetry, and that sort of needs to hold also on neutral terms. And so that we have some idea about how to implement that by doing some sort of munging of neutral terms, basically, which has been done in other contexts to sort of implement associativity of list concatenation definitionally, or sort of things like that. You have some sort of law that holds on concrete constructors definitionally, and you make it hold on neutral ones too by sort of munging your neutrals. So that's a long answer, maybe. We have some ideas, basically, and some experiments.
They're work in progress.
Yeah.
Okay. Folks, I'm going to wrap it up a little bit early here and refer you to the Zulip for further discussion, because people might need a 5-minute break before we go on to Andre Bauer's magic show, which I think most of you are aware of. Andre is going to pull a rabbit out of a hat at the Topos Institute in about 5 minutes. So that gives us 5 minutes to thank Mike and applaud for his great series of lectures. Mike, thank you so much for sharing these ideas with us. It was really exciting, and I look forward to learning more about this work from you and Thorsten and Ambrose as well. Really, congratulations, you guys. This is terrific work and a nice series of lectures. Mike, thanks again.
Thank you for the invitation and the opportunity. I appreciate it a lot.
Stop recording and say goodbye.